8.8 in your textbook, optimum volume and surface area. So we're talking about trying to determine and apply optimum measures to solve problems. So the first example says that we have a 600 centimeters squared of material. Determine the maximum volume using 1, a square-based prism, and 2, a cylinder. So this lesson is actually very similar to the lesson when we talked about maximum surface area. You guys remember that? We talked about the least amount of perimeter, and we talked about the maximum amount of surface area. So
no, was it area and perimeter?
Sorry, Michael?
Was it area and perimeter?
Area and perimeter, yeah, sorry. So we talked about a square being a rectangle that provides the maximum amount of area with the minimum amount of surface area, the minimum amount of perimeter. Okay, so this lesson is kind of like the 3D version of that lesson. Okay, it's exactly what it is actually. We're talking now, rather than a 2D figure, we're talking about a 3D figure. Okay, so we now want to find out what is the minimum amount of surface area that we can use, or material, for all sides of this cube, and obtain the maximum amount of volume. Okay, so we did mention it before in 2D shape. The shape that provides the maximum amount of area with the minimum amount of perimeter is a circle. Who can tell me what that would be in 3D terms? What would be the shape that would provide the minimum amount of surface area for the maximum amount of volume? Yeah.
A sphere?
A sphere, good. So just like a circle does so for 2D, a sphere does so for 3D. Okay? So if you can kind of extrapolate information from the 2D, we can kind of have a pretty educated guess on what type of shape would provide the maximum amount of volume per minute on the surface area. So in terms of a rectangle shape, what would be the 3D shape that would provide the maximum amount of volume if we're talking about rectangular prisms? Austin? A cube, right, exactly. So just like a square provides the maximum amount of area for perimeter in 2D, a cube provides the maximum amount of volume for surface area in 3D. Okay, so it's important that you understand how these two lessons are related, because it'll just give you much more kind of conceptual background on what we're doing here. So it says, given 600 centimeters of material, determine the maximum volume using a square-based prism and a cylinder. Before we even do that, who can tell me which one is actually going to give us more volume? A square-based perimeter or a cylinder? Which one do you think? Matthew?
A square-based perimeter.
Okay, why?
Because a square gives.
So remember what we're comparing here then. You're comparing this, which is a square-based prism, to a cylinder. Okay, which one could possibly you gain the maximum volume? David?
A cylinder.
Okay, why?
Because a cylinder has a sphere, like has a circle in its base.
Yes, exactly. You're right. So the reason why it's actually going to be a cylinder is because a cylinder actually is able to approach kind of the shape of a sphere closer than a rectangular based prism, right? Because of that surface area, that maximum use of the perimeter of the circle. So we're able to actually establish more volume using a cylinder than a square-based prism. But we're going to find that out now in a second, Mike.
Well, doesn't it matter if one shape is bigger?
It does matter the dimensions, yes. So for instance, a cube, something like this, is going to provide more volume than a cylinder like this, right? Because there's a lot of surface area going into creating this particular shape with not a lot of volume being contained within it. So you're right, the dimensions do matter, but if you had to choose one or the other and you could adjust the dimensions to however you like, you definitely would choose a cylinder as opposed to a rectangular prism. All right, so square-based prism is the first thing. We want to find out the maximum volume using a square-based prism. So what this question is asking then, we've already told us that it's a square-based prism. So that means the base is a square. It doesn't tell us that the height is the same as the base. So really what we're trying to identify here is, what is the value of the height for a square-based prism with this amount of material? Okay, so that's what the question is asking us. What is the height with this amount of material, and what gives us the most volume? Okay, so if here's my square base prism again, what is my value of H, okay, that gives us the most volume, max volume, with a surface area equal to 600. Okay, so those are our parameters. These are set. 600 centimeters squared, our maximum volume, and we don't know our value of H. So what we've done here then is we've used our surface area formula for a square base prism. I'm just going to go through this quickly to explain it, right? So we have a surface area of a prism. We don't know that this is necessarily a cube, so we can't assume that this value of H here is the same as the value of S. Okay, so to find the surface area for this object then, we need to do 2 times S squared, so that's the base, S times S, that's the area of the base. And there's 2 of them because there's a top and the bottom. And then it's 4 times S times H, right? So we don't know what H is, but we know it's going to be the same on all 4 sides. Okay, so that gives us our surface area of that particular object. Any questions about that formula? Okay, that's the hardest part with this question, really. Okay. Now what they've done in the textbook is they know the they know the surface area is constant at 600. So what they've done is they've plugged in 600 for the surface area. And now they've rearranged this formula so that it's in terms of H. So see what the actual value is here? H is equal to 600 minus 2s squared. 2s squared coming to the other side, all divided by 4s. Okay, so that's how they developed that formula for height. So now when we choose this value of s, we can figure out our height. Okay? And the reason why, again, that these are both set and they're tied together is because the question tells us we have to have a surface area of 600. So if I'm going to choose this height of 6, well, I have to calculate what my height's going to be to maintain a surface area of 600. Does everyone understand that? Everyone get this table? Okay, and now the volume, finally, the volume for the surface area, again, is going to be the area of the base, so S times the height. So that's where S squared times H comes in. And again, you're going to use this value for H and this value for your side length. So when we do that, we can just sub in different values for the side length, and we see this pattern that evolves of kind of this increasing volume, and then it starts to decrease. Okay? And that allows us to find out that this value right in here gives us our maximum volume. So our side length of 10. Okay, so our side length is 10, our height is 10. We've actually proven what we actually talked about in the beginning, that the shape that gives us the most volume in terms of rectangular prisms is a cube. Okay, and that's where it's proven right here. Our side length is 10 and our height is 10, gives us the most volume. Any questions? Doesn't matter what we would have chosen here. If we chose 900, 1200, we would have found out that the side length and the height have to be the same to produce the max volume. Okay. All right, so now that's square base prism. Now we're looking at cylinders. So we need to figure out now what the dimensions of the cylinder are to give us the maximum amount of volume for that cylinder, given, again, a surface area of 600. So we go through the same process. The surface area for a cylinder is this formula, okay? And that's because the top and the bottom circles are 2 pi r squared. Pi r squared is the formula for area of a circle, and there's 2 of them. So pi r squared, so there's 2 pi r squared. And then this calculation here, this is for the sides. If you imagine the sides of this cylinder being unraveled, if we took a scissor and we cut right down the middle and unraveled it, what we get would be, we get a rectangle like this, right? If we take a piece of paper that's a cylinder, like this, we cut a slice right down the center of that cylinder, we unravel it, we get a rectangle, okay? Where this dimension, if you look closely, see that dimension? That's the circumference of the circle. Now it becomes the width of my rectangle. Okay, you guys see that? So the surface area then of this cylinder becomes the circumference of the top circle, which is 2 pi r, times its height. Okay, that gives us the surface area of the cylinder. All right, that's where that formula comes from. All right, so once we have that formula, which is here. We plug in surface area of 600, that's the given value, and we rearrange again for the height. Okay, so just using algebra, we rearrange it for height. Okay, yeah.
Why'd you do plus 2 pi r squared?
I mentioned that at the beginning. That's because that's the top surface area of this circle.
Oh, it's the surface area. Okay.
Yeah, and the bottom surface
Because
area
you
of
were
that
talking
circle.
about the circumference, that's what I thought. Why'd you add one more?
No, this is the circumference, 2 pi r, times the height, so that's the sides of the cylinder,
Yeah.
and then this is the top and bottom. Okay? All right, so once we rearrange it for height, we do the same process. This time, we're just providing values for r. These values here are made up, these values are calculated, and then the volumes are calculated. Okay, so again, we get a graph that's similar. You can see a more detailed graph in the textbook, but we get this pattern, this parabola pattern, where it goes up and then starts to go down. Okay, and what we find out then is that this value here gives us the max volume. Okay, and what you should notice then, but this radius and the height is the radius is half of the height. Or in other words, the diameter of the cylinder has to be equal to the height for max volume. Okay, and it's not exactly on, this gives you 11.2, but that's just to show you if you were to put in the actual height and radius to be exactly the same, you'd get a little bit more volume out of it. So that volume is not actually quite the max because the radius is not exactly half of the height. Which makes sense, right? If you draw it out, now